Robot peg-and-hole assembly is a challenging task requiring precise localization. Inspired by human learning, peg-and-hole skills can benefit from the simpler inverse peg-out-of-hole task. The key concept is the robot first learns peg-out-of-hole skills using reinforcement learning. A set of sampled peg-out-of-hole trajectories, consisting of kinematic, visual, tactile observations and robot actions, is then reversed to generate training data for peg-and-hole policy learning. We construct a common environment for both peg-out-of-hole and peg-and-hole tasks. First, the peg-out-of-hole skill is learned using reinforcement learning with robot kinematic, visual, and tactile information as inputs. Then, we can collect a large data set of peg-and-hole trajectories via reversing and regenerating the peg-out-of-hole trajectories. Finally, the data is used to train a peg-and-hole policy with RL in the same environment with the peg-out-of-hole task. In this work, we use an ABB Yumi robot equipped with 4 Gel-Sight-like vision-based tactile sensors on its fingers and an Intel RealSense camera mounted on its body. We designed 4 kinds of peg-and-hole objects: red cube, red cylinder, red hexagon, and white cube. To validate the proposed method, we firstly conduct the peg-out-of-hole to peg-in-hole policy learning experiments in simulation. These videos show the learned peg-out-of-hole and peg-and-hole skills. Ablation experiments removing either visual or tactile input show that the proposed multimodal method improves peg-hole approach, adjustment, and insertion while reducing contact forces compared with single-modality baselines. When obtained the peg-and-hole policy, we conduct the sim-to-real transfer experiments combined with tactile simulation calibration and visual domain randomization. These videos show experiments in the real world. Our method achieves the highest training reward and success rates compared with direct RL method that trains from scratch in single-modality methods, which demonstrate the effectiveness of our framework. In summary, peg-and-hole skill gains useful experience from peg-out-of-hole tasks. We propose a novel visual-tactile skill learning framework for efficient peg-and-hole assembly, with a key module of peg-out-of-hole to peg-and-hole policy learning. Extensive experiments demonstrate its effectiveness and generalizability over other baselines.